very kind introduction, and this may not be my first, well, this may be my third visit to India. And once before I received the Nobel Prize, but twice after. And I'm glad to tell you that so this institution, you know, of so high level, and I get to, without any reluctance, I get to discuss my topic on the right-hand side, and in most cases I'm asked to discuss the chemistry on the left-hand side. That gave me the Nobel Prize, together with Heck and Suzuki, Professor Heck and Suzuki, in 2010. But today, I would like to discuss the chemistry for the future, maybe. Well, for us it is the current. So that's what I want to do. Okay, so I am not going to discuss this one. I realize that most of you are thoroughly familiar with. But if I remind you, so in trying to develop this cross-coupling, we learned the tremendous power, catalytic power, ability of the D-block transition metals. So I may very briefly discuss why D-block transition metals. But then my main discussion is on organo-zirconium chemistry. Zirconium itself is a D-block transition metal. And we use this for asymmetric synthesis, which we have been doing over the past 20 years. And by now, I rather boldly, or I mean, without hesitation, I declare that we have conquered the ultimate level of asymmetric synthesis, and that has, you know, through the use of a D-block transition metal catalyst. And that's the main topic of my talk today. Okay, so well, spending maybe 5 to 10 minutes, let's talk about how to synthesize any key important word is any organic compounds in high yields and efficiently, selectively, economically, safely. Then if you link the first letter, Y-E-S, E-S, yes, yes. I'm still looking for the second Y word. Then I can say, like Obama, yes, yes. But I'm not a politician, so I can live without the second one. Y words are very scarce, as you know. Anyway, so what I mean by this is the green chemistry. And briefly, we should consider all usable element, and the number is rather limited, 70. By avoiding radioactive elements, it's very difficult to be safe. Inert one, very difficult to do anything, as you know. And inherently toxic elements, there are up to 10 or so that we should normally stay away from. I'll show you next slide. And if desirable necessary, consider their binary combinations or ternary combinations. So that's what I have been trying to do, investigate, look into, in all cases. Use metals for desirable reactions, even though organic compounds, by and large, do not contain much metal. Actually, they do contain a variety of metals in minute quantities, as you know. And I believe that this last sentence, last one is the most important. in my lecture today, use transition metals mainly as catalysts. The transition metals are fantastic sources of catalysts, and I may briefly touch on that. I may not because of time. Okay, anyway, I can say that. And in my special topics course on organo-transition metal chemistry, which I started teaching at Syracuse University, without knowing much about it, I thought this might be an interesting topic for my special topics class, about 10 to 20 students. And this turned out to be a very excellent learning process. And through teaching, I learned, and through learning, I generated my own research subjects. Okay, now everything that you know, all of you know, there are 113 or so elements known. Probably number will eventually increase, but very slowly. So that's enough, because most of the last ones, they're all radioactive. And as I just told you, we by and large stay away from them. So eliminating those, there are of the 113, about 10 of them, close to 10 of them are inherently toxic. 7 shown here, but inherently toxic. Beryllium, cadmium, all Japanese know this Ei-ichi disease, in middle part of Japan. As they live and drink water and so on, their bones start aching. And apparently it's due to the presence of cadmium. And mercury, Minamata disease, you may know. Japanese have suffered from all these difficulties. This mercury. And down in Kyushu, thanks to this industrial, pollutants, fish started jumping, going crazy, and then they would even die. So through this, they traced down to this mercury poison. And mercury is important. We can, as long as we trap it in a thermometer and so on, then that's a wonderful element, wonderful metal. But as a research, the synthetic element used in organic synthesis, I don't recommend that. I would scrupulously stay away from it. And there are thallium, lead, and tin. Professor Stille's tin, which came after my cross-coupling. And then to my chagrin, this organo-tin Stille coupling became swept all over America, and eventually, spreading into the entire area of this planet. But I don't think that we should consider tin for cross-coupling, because it's very difficult to avoid its toxicity. In very extreme cases, we may still use. And then, of course, this AS, how do you call this? Yeah. Anyway, the milk containing small amount of this caused major difficulties in Japan and other areas perhaps. So there are 7 shown here. And excluding these, I outright exclude them. So I'm sorry, I outright exclude the Stille coupling, which I discovered first. He negotiated with me, and then I said, because I learned that the tin is toxic, I'm no longer using it. He smiled. 1981, and then he already had, he had just done a run. And then he became the world leader. Very unfortunately, he passed away. But aside from that, I don't think that we should be considering 10 for even cross-coupling or other reactions. Anyway, so having excluded all these, how many elements are still available? Well, there are these blue ones. These are main group metals, 20-some. And then, of course, about 10 of them, I consider them to be organic elements. In other words, organic, so-called organic compounds. They tend to contain these elements. Besides carbon, of course, and hydrogen, and these 11 shown. These are the main components of organic compounds. So I urge all of you, particularly young people, to actually become very thoroughly familiar with these, good and bad include both. And these are the toys for chemists, tool materials for the chemists. So we might as well become thoroughly familiar with this. So in my class, special topics class, I urge all my students to become familiar with, and I sing a song for the 18 or so main group metal up here. It goes like this. Here's hydrogen and helium. Liebe Bocanioxy Flunion completes the first row. Namagal C4 Chloral. These are the first 18 members of the table. Now I know them all by heart. I don't want to memorize anymore. I force them to memorize these 18 elements that way. And then, of course, we know that we have to, we learn that, so vertically arranged ones in one group, they have something in common, important, chemically important in common. I think we should do that. We should learn this that way. But what I have been emphasizing the most in teaching and also, more importantly, my own research are the so-called D-block transition metal. D-block transition metal. 3 by 8 minus 1, technetium, artificial element, and intrinsically radioactive function. Okay, so these are the ones that you want to be, to become very, very familiar with, and I will be talking about them today. Okay, so having learned that, now I want to remind you, so here in St. Petersburg, it's confusing, but it's called Moskovsky Avenue. So Moscow and St. Petersburg. Anyway, here is a bronze statue of Mendeleev, my great hero. And already more than 150 years ago, in the middle of 19th century, he knew all these elements. Not only knew, he arranged in the most scientific, chemically correct scientific way. Of course, that's the origin of the periodic table. And surprisingly, there are 91 or so shown here. I counted, maybe off by 1 or 2. Forgive me. 91 elements. And of 91, he discovered 11. More than 10% of the universe, I would say. Okay. Madame Curie discovered radium and curium, first with her husband, as you know. and then the second one with her daughter and the daughter's husband. And for these activities, she received 2 Nobel Prizes. One of very, very, very few individuals. Nobel Prize winners of among the Nobel Prize winners. Now, knowing that, I felt when I went there and then learned all this about, there's an old lady who are middle-aged maybe. Every time I go there, I've been there 3 or 4 times, she would spend 2-3 hours explaining scrupulous, in excruciating detail about Mendeleev. But I always do that, visit her. And one of the most astounding features of his career is that discovering 11 elements, about 10% of the universe, he predicted if there should be, because he made this framework first, and he saw many holes. If there should be an element here, if it is found, discovered, then it should have this such and such density and some chemical prediction, chemical properties should be this way, that way. He predicted. With those predictions, he looked for them, and then he discovered the 11 of them. So that's why I say I want to give him 11 Nobel Prize. Anyway, so one thing I realized when I was a graduate student at University of Pennsylvania, and that was how difficult organic synthesis was. I was an organic major. First year, I learned many things, mostly spent in lecture room, learning from my professors. And then I thought I learned a lot about organic chemistry. Then I realized that how difficult and how limited organic synthesis back then was. When I became a second-year student, and I spent 3 years for my PhD degrees there, and I was a super student. I shouldn't say brag myself, but accept my facts. And I got 8 consecutive excellent marks in so-called cumulative examination. You don't know what kind of questions are given. So you have to sort of try to jack up your foundation of chemical knowledge and so on. And I was so proud, and I thought that I would be able to do almost anything in organic chemistry. Then I went into the laboratories, and I was a miserable failure. Miserable failure. Many things, essentially most of the things that I thought should work would fail. And just one time, my wife, I was newly married back then, came to the lab, my lab. And that's the time when I had a boom, mini explosion. She would never come. I think that's better. Anyway, so instead of blaming my, inefficient and unskilled experimental technique, I blamed to the chemistry, state of the art back then of organic synthesis. Why is organic synthesis so difficult, and roundabout? You're familiar with acido-acidic ester synthesis, malonic ester synthesis. You bring a somewhat complex molecule, you modify this, and then you blast off whatever you don't need, And I started blaming. It's not me. It's the state of the synthesis back then. That was at 4. So I began thinking, we should simplify. We should simplify organic synthesis, and so that anyone can just do it. I thought about this, and at that time there was this Lego game invading United States and subsequently all over the world, and that originated from Denmark, as far as I know. In a Lego game, literally they do this kind of thing with little toy pieces. So this is what you want to build up. And then you chop it into here and into this one. And one has a hole, that's acid, electron deficient acid. One has a stick with 2 electrons, that's a base. So acid and base, and you snap it. You snap it, then you get this one. So as long as you know what you want, and as long as you know this kind of simple structure, then you chop it, and make this, and then snap it. Shouldn't this be a way of synthesizing variety of organic compounds? So ignorance is sometimes a powerful tool. So I started thinking about this, and then I found a miserable state of the art back then. So these are representative organic compounds containing metal, because I wanted to have R1 minus. And these are representative organic compounds containing R2 here in the form of R2